Example 8.19. A satellite orbits the Earth at a height of 400 km above the surface. How much energy must be expended to rocket the satellite out of the Earth's gravitational influence? Mass of the satellite is 200 kg. Mass of the Earth is 6 into 10 raised to 24 kg. Radius of the Earth is 6.4 into 10 raised to 6 meter. G is also given. Now height of the satellite is 400 kilometer, that can be written as 0.4 into 10 raised to 6 meter. Mass of the satellite small m 200 kg. Radius RE 6.4 10 to the power 6 meter. Mass of the Earth is given, G is given. Now see, energy required to send the satellite out of the orbit is nothing but the binding energy, rather negative of binding energy. So it becomes positive, and binding energy of the satellite is nothing but minus G MEM upon 2 times RE plus H. Now if you take negative of this, then this becomes positive, that is positive G MEM upon 2 into bracket RE plus H. Now just you have to place all the values and simplify, you will get the answer. Okay, mass of the Earth is given, small m is 200 kg, RE is 6.4 10 to the power 6, H is 0.4 10 to the power 6. So simplify and you get the answer of this question. Okay, 5.9 into 10 raised to 9 joule. Okay, now we have the next numerical 8.20. Two stars each of one solar mass. One solar mass is 2 into 10 raised to 30 kg, mass of the sun, are approaching each other for a head-on collision. So these are the two stars. Okay. Now they are initially at rest and they are approaching each other. Okay. Means coming towards each other for head-on collision. When they are at a distance 10 to the power 9 kilometer, their speeds are negligible. So initially, okay, their speeds are negligible. Okay, 10 to the power 9 kilometer is the initial distance. So R is equal to 10 to the power 12 meter, we can say. Okay, so speed is negligible, means initial kinetic energy is 0, we can say. No speed as such. Initially they were at rest, we can say. What is the speed with which they collide? The radius of each star is 10 to the power 4 kilometer, means 10 to the power 7 meter. Assume the stars to remain undistorted until they collide. Okay. Now see, this is the figure which is explaining the initial condition and final condition. Okay. See, initially they are at distance 10 to the power 12 meter. Their distances are taken from the center. Their masses we consider as m. Both are same stars which are having the mass which is equal to the mass of the sun. Now radius of these stars is also same, that is r. Okay. Initial velocity of both the stars is equal to 0 and they start approaching each other. And this is the final condition when they collide. So distance between their centers will be 2r now, 2 times radius. Okay. Now this is explained here. Initially no velocity. So initial kinetic energy is 0. So it has only initially potential energy, and that will be minus G m into m upon r. So minus G m square upon r will be the potential energy. So total energy initially will be equal to minus G m square upon r, because kinetic energy is 0. Now let us consider that when they are colliding, their velocity is v. Okay, one is having velocity v, the other is also having the same velocity, because they are having the same situation initially. So their kinetic energy at the time of collision, that of each, is 1/2 mv square, that of one, and the 1/2 mv square of the other. So total kinetic energy will be 1 by 2 mv square plus 1 by 2 mv square, that will be equal to mv square. Okay. Potential energy will be minus gmm upon the distance between their centers, that is 2r, which I have explained. So it can be written as minus gm square upon 2r. Okay. So finally we can have total energy at the time of collision will be kinetic energy plus the potential energy, and that will be mv square minus gm square upon 2r. Okay. Now from the law of conservation of energy, initial total energy and final total energy must be equal. So we are comparing the initial and final energies. Okay. Initial energy in the beginning was minus gm square upon r. Finally we have just now calculated mv square minus gm square upon 2r. Okay. Now on simplify, you can easily calculate mv square is made subject of the formula. Okay. mv square is made subject of the formula. So this gm square with negative sign is taken on left hand side. Okay. And then gm square is taken common, 1m is cancelled out. You can easily now simplify this part. Okay. This m can be cancelled out. Okay. 1m goes out. Okay. This is taken, this gm square upon 2r is taken on left hand side. Okay. So it has become positive. Okay. So it becomes gm square upon 2r positive. Then minus gm square upon r is already there. This mv square is made as subject of formula. Now m is cancelled out. Okay. So v square can be written as, okay, gm into bracket 1 upon 2r minus 1 upon r. And just we have to place all the known value and simplify. G is known to us, mass of the star is given, okay, 2 times the distance between the stars, okay, after collision, okay, that is 2 times radius, rather we have to place. Then r is initial distance between the stars. Simplify just and get the answer for the speed, that is about 2.6 into 10 raised to 6 meter per second, okay, at the time of collision. Numerical number 8.21. Two heavy spheres, each of mass 100 kg and radius 0.1 meter, are placed 1 meter apart on horizontal table. So we can say that this is the table on which the two spheres are placed, which are having same mass, that is 100 kg. Okay. What is the gravitational force and potential at the midpoint? This is the midpoint of the line joining the two centers of the spheres. Okay. So the distance is taken from the center. Okay. This is 1 meter. Is an object placed at that point in equilibrium? If the object is placed here, whether it will be in equilibrium or not. If so, is the equilibrium stable or unstable? Mass of both the sphere are same, 100 kg. We consider this point O as a midpoint. This is point A, this is point B. AO and BO, both the distances will be same because O is a midpoint, that is 0.5 meter. Okay. Now mass of object placed at O is m. We consider that the mass of the object which is placed at midpoint is m. Then the gravitational force of sphere A and B, we can calculate F is equal to gm1 m2 upon r square. So G, mass of the big sphere capital M, into small m upon half of the distance between their centers, that is r by 2 whole square. And this capital M is 100 kg, small m is not known, that we have placed. Okay. G, then this becomes 0.5 because half of the 1 meter is 0.5 meter. So that is the force in OA direction, the attractive force. Okay, so the direction of force will be in the OA direction. This is say A, this is B, and mass M is placed here. An attractive force will be in the direction of OA, this direction. OB, that is force by B, will be in the right hand direction. Okay, one is in the left hand direction, the other one will be in the right hand direction. Same magnitude you will get because the other object is also of 100 kg only. Okay, so next force is same, that is force due to B. Okay, so two equal and opposite forces are acting on this object which is placed at the midpoint. So the force will be 0, not net force will be 0. So the body is in equilibrium. Now if the body A or B is displaced, either A or B, not both, a little towards either mass body from its equilibrium position, it will not return back to its initial position of equilibrium. Okay. So if A or B is displaced, either A is displaced or B is displaced, then this body initially was in equilibrium, will not come back to the initial position of equilibrium, or we can say the body is in unstable equilibrium. If distances are same and the body is arranged according to the initial position, then it is going to remain in equilibrium. But if A or B is displaced, then this will come in the unstable equilibrium. Now let us calculate gravitational potential. Potential is minus Gm upon R. Okay, R is the distance. Okay, so minus Gm by 2. Rather, this should not be 2. Okay. So the equation of the gravitational potential as such, try to understand. Here it should be minus Gm upon R. This is not 2, it is R only, distance of the midpoint from A and B. So gravitational potential, because of the first sphere, okay, that will be minus Gm upon R, and R is 0.5. Second will also have its potential minus Gm upon R, R is 0.5. So total potential will be the sum of both the potentials, that is VA and VB. So it becomes V is equal to VA plus VB, you can see easily. Okay, and VA and VB both are same, so total potential V is equal to minus Gm upon 0.5, okay, minus Gm upon 0.5, okay. So it becomes minus 2 times Gm upon 0.5. Here also there is a misprint, it is not 0.2, it is 0.5, okay. So it becomes minus 2 times Gm upon 0.5. Just place the values. Okay, G is known to you 6.67 10 to the power minus 11. Mass of the object, either A or B, both are same, 100 kg. So you will get the potential at a midpoint to be minus 2.7 into 10 raised to minus 8 joule per kg. Okay, negative sign indicates that equilibrium is unstable. Okay. Here we are completing all the numericals. Try to calculate all the numericals in your notebook 2-3 times and learn them. Okay, thank you very much.